6.2, exponential growth and decay. So first of all, we have exponential growth, where I'm just going to informally define this as something is increasing over time by a common ratio. Okay, so growth means we're going up, and because it's exponential, we have a common ratio. Versus exponential decay is going to be decreasing over time by a common ratio. Now, if something is going to be increasing over time, do we think that that common ratio should be more than 1 or maybe less than 1? So I'm thinking probably where that b value is going to be greater than 1. So we're talking about doubling or tripling or quadrupling. So times 2 or 3 or 4. Versus exponential decay, something is decreasing, so getting smaller. So maybe we're multiplying by 1/2 or 1/3 or 1/4. Okay, now to go along with that idea is we actually have an exponential growth function. In our exponential growth function, we have y equals a times 1 plus r to the t. Now, starting out with some of these variables, I'm going to start with t, which is going to represent our time. Time is most commonly in years. Then we have r, which is our common ratio, or in this, our growth rate. Now, commonly, we use these for story problems, and if we're talking about a growth rate in a story problem, we're usually talking about a population, and they're going to give us some sort of like a percentage. So it's going to increase by 15%, or it's going to increase by 10% or 20%. So just keep that in mind, and then we're going to add 1 to it. And then A, I usually just define as our start or starting value, which if we're talking story problems here, that's our starting population. So did the population start at 100 people, 200 people, etc., but that's your starting value. Now, exponential decay function, everything is still the same here. A is still your starting value. R is still your common ratio, except this time instead of calling it a growth rate, we're going to be calling it a decay rate, because this time you're going to get a keyword as of decreasing or going down. T is still your time. Okay, the difference here is in exponential growth, we're going to add 1 to our growth rate, versus exponential decay, we're going to subtract 1 from our growth rate. Example 1. A website has 500,000 members in 2010. The number Y of members increases by 15% each year. Now, key word here is increases. So that is going to be exponential growth. The population is increasing. Part A, write an exponential growth function that represents the website membership T years after 2010. Now, if we're doing it after 2010, that tells me that we're starting in 2010 as our starting point. So, growth function, y equals a times 1 plus r to the t. So, we're going to have y equals. Our starting population is the population in 2010. Well, they told us that that was 500,000. So 500,000 people, and then 1 plus R. R is our growth rate, which is 15%. Now, keep in mind when we're dealing with percentages, we typically don't just stick in 15. So we have to look at 15% as a decimal. So if we forgot, we can just move the decimal, but the long way of doing that is we have 15%, which equals all decimals are, all percentages are based out of 100, so that's really 15 out of 100. which means if you grab your calculator and take 15 divided by 100, you're going to get 0.15. So 15% as a decimal, 0.15. That is what we're going to substitute into the function. And then it says as a function of t years, so we're leaving the variable t. Now, if you leave it like this, I am personally fine with that, but more commonly, you're probably going to see y equals 500,000, and then you actually take 1 plus 0.15 and get 1.15 to the power of t. So this would be your answer for part A, which is your growth function. Now, part B, how many members will there be in 2016? Round your answer to the nearest 10,000. Now, how many in 2016? We have to consider where we started. If I started in 2010 and I went to 2016, that is 6 years later, which means my time period here is going to be 6. So I'm going to figure out y equals 500,000 times 1.15 to the power of 6, because from 2010 to 2016, we're talking 6 years later. Pause your video, grab your calculator. I'm going to grab mine. I'm going to take 500,000 times 1.15 to the power of 6, which is getting me, wow, I believe that's 1,156,530.382. But they specifically said round to the nearest 10,000. So this is 1, 10, hundreds, thousands. This is thousands. This is 10,000s. So if we look backwards, the 6 is 5 or above. Give it a shove. So we're going to have 1,160,000, and we're just going to round that off. People, members, 500,000 members. Which essentially, another way of writing that, because we had to round it to the nearest 10,000, you could say 1.16 million members, because this is our million, or you can read it as 1,160,000 members.